Hello everyone. A very good evening. I hope I'm audible and visible. So, any one of you can confirm it. So, let's wait for 5 minutes so that everyone can able to join this session. Okay, let's start the session. Hello everyone. My name is Pooja Verma. I am PMRF Research Scholar from IIT Kharagpur, and instructor for this course is Professor Shantanu Chattopadhyay, Electrical and Electronics Engineering Department, IIT Kharagpur. This is a week 4 live interactive session on digital circuit. For asking and interacting, you can use the chat box, or otherwise if you have no doubt, you can unmute yourself and ask questions. Okay. Okay, these are the topics which have been covered for this week. So I hope all of you have gone through this video lecture for this week. This week. So the outline for this week content are conversion to the NAND gate, conversion to NOR gate, exclusive XOR gate, XNOR gate, parity with generation, and checking CMOS inverter, noise merging, timing diagrams, hazards, and glitches, arithmetic circuits. In arithmetic circuit, the topics has been covered, that is adder, subtractor, carry, look ahead, adders. Okay, so let's move some problems which is very similar to your assignment questions. So it may be helpful to you to solving your assignment problem. Okay, so first question is, consider a 4-bit adder with inputs A3, A2, A1, A0 and V. B is also considered 4-bit digit, that is B3, B2, B1, B0, for which of the following input condition no carry out would be generated. Assume there is a no carry input. So would you like to solve it first? Just we need to add these two bits and see in these options which are generating no carry. But I think this question is can be there is carry output condition will be there only. Okay, so let's first we will go by options because we need to check in which input condition there is a no carry out would be generated. So first option A is, that is 1 0 1 1 and 0 1 0 1 1 1 0 1 carry is there, right? The carry would be propagated to the next, that means here. So again 110, again 1 carry will be there, so carry will be added to the next 110. Again carry is there, so again 110 and there is a 1 carry will be there. Okay, this one is carry. Then move to the option B, 1 0 1 1 and B is 000. This one is 0. So again add 110 and again carry will be propagated to the next bit. Again 110 and carry is propagated to the next bit for option A. And there is 0 0, so 0 0 is 0 plus 0 is 0 and 1 carry is there, so 1 will be there. Okay, and again 1 and 0 1, so there is no carry will be there. Okay, now move to the option C. So option C is again 1 0 1 1 1 0 1 1 and B is 0 1 0 0. This is 0. So 1 0 1, again 1 0 1, 0 1 1 and 1 0 1. In option C is also there is no carry is generated. Now next to the check in option D whether there is a carry out is there or not. So A is 1 0 0 1 and next one is B 0 1 0 1. Add these two bits and let me know answer in the chat box. The option A is correct, it is given, but let me know how. Again 1 1 0 will be there, 0, so 1 carry is propagated to the next, there is 1, again 1 0 1 1 1 0 1 and there is no carry out in option D also. Okay, so check what the question is saying. Question is saying consider a 4-bit inputs A and B for which of the following input conditions no carry out would be generated. But from here we can see that in B, C and D, in these options there is a no carry is generated. Only option A is generating the carry. Okay. In that case option A is correct. But in the question there is no will not be there. Okay, for which of the following input condition carry out will be generated, because yeah, otherwise you have to take B, C and D. In these three conditions there is a no carry out generated. Okay, if carry out is generated only option A. Okay, so there is a mistake in question, so no will not be there. Okay, so option A is correct in that case. Otherwise, if multi option is there, then you have to tick B, C or D. Okay. Okay. So I hope all of you understand this. So moving to the next question. So next question is, which one of the following expressions does not represent exclusive NOR of A and B? So which one of the following exclusive NOR means XNOR, right? What is the expression for XNOR gate? What is the expression? That is A, B plus A dash and B dash, right? This is the expression for XNOR gate. Yeah. So let's check which one of the following expression does not represent exclusive NOR of A and B. So it is also option A is representing the XNOR gate. So this one is correct. Now next option B is A dash XOR with B. So if you solve this further, you will get first we need to write what is the XOR gate. XOR gate is normal A XOR B. I am writing here A dash B, right, plus A B dash, right, XOR gate. A XOR B is represented by this one. So if we want to write in this form, so what we can write here, a bar is already there, so in that case a double bar will be there because a bar b, so a bar b, so a double bar b plus a dash. Now what is it? A only and b dash. So a is here in a dash, so a dash b dash. A double dash will be a only, so it will be a b plus a dash and b dash. So option B is also representing the XNOR gate. So option B is also correct. Now move to the next option C. Option C is A XOR B dash. So again we can expand it A XOR B dash. So what will be the A dash B only. So here B is B dash, so B dash will be same. Now next is A and B dash, so B double dash will be there. So B double dash will be B only because that will double dash is cancel out. A dash B dash plus A B. So option C is also representing the XNOR gate expression, right? So option C is also correct. Now object on option D. So option D is A dash XOR B dash, right? Now expand with this A dash means A double dash B. So B is B dash plus A. A means A dash and B dash. So B double dash will be there. So it will A double dash will be A only, right? So A dash B plus A dash, again double dash will be cancel out. So A. So what it is representing A XOR B. So that means option D is not representing the XNOR gate. So in the question it has been asked that which of the following expression does not represent the exclusive NOR gate. That means option D is the correct option. Option D is not representing the XNOR gate. Okay. Okay. So I hope all of you have got this question. Moving to the next one. So yeah. Next question is when two 8-bit numbers A7 to A0 and B7 to B0 in 2's complement representation with A0 and B0 as a LSB least significant bits are added using ripple carry adder. The sum bits obtained are S7 to S0 and the carry bits are C7 to C0. An overflow is said to have occurred if, in which condition the overflow will occur? Option A, the carry bit C7 is 1, all the carry bits C7 to C0 are 1, or option C, A7 B7 S7 dash plus A7 dash B7 dash or S7 is 1, and option D, A0 B0 S0 dash plus A dash A0 dash B0 dash S0 is 1. So already you have studied that the this is a 8-bit, right? This is question only which I am reading. Now I am going to explain it. This is the question: when two 8-bit numbers A7 to A0 and B7 to B0 in 2's complement representation are added using ripple carry adder. Okay, so you have seen that ripple carry adder, there is a full adder is there, four full adders are added, and here the a two bits are given to all. I'm just giving it, and there is C in, and the carry of this adder is going to the next adder, right? So there is 8 bits, so 8 full adders will be there in that case. So can anyone tell me that in which, when will overflow occur? Overflow occur in the last bit only, right? Not in the first bit. For example, we have seen in the first question, yeah, from MSB only overflow will occur. We have seen in the first question as, for example, I am giving one example, 0, right? So if 0 0 1 1 0, here one carry is there, so in that case here that overflow will not, because that carry bit will be added to the next bit. Okay, so again 1 1 0, right? And one carry will be propagated to the next one, so again 1 1 0. So there must be only 4 bit place, but one here one bit will be extra, in that means that is overflowing. Okay, so that extra bit is called overflow. So this one is example. So that means if we are taking the 8 bit, so 8 bit, in 8 bit only in the last bit, that means A7. A0 is LSB, least significant, and this is A7. This one is called A7 if there is a 8 bit, this side. So only in this bit overflow will occur, A7. So we can't take that in the LSV, least significant bit, that overflow can't be occur. So only last bit overflow will occur. Okay, so what will be the conditions in which overflow will occur? Let's see that. Okay, so the cases when overflow will occur if both B7 and A7 are 1, right? If the other cases are also possible, well, bits are very large, so just taking, in order to make the condition, we are taking this. Let's see. So if A7 and B7 will 1, so I'm writing here A7, I'm just writing so that A7, A6, A5, A4, A3, A2, A1 and A0. B7, B6, here this side B0. And similarly, some will generate S0 to S7, S6 and S7, right? And there may be, if we are adding these two, so maybe there will be carriage also generating. I am writing here opposite C0, C1, that is carry. That is C7, S6, right? Carry number 7, 6 and carry number 7. Okay. So these the overflow will occur in this condition if A7 and V7 both are 1s. In that case, the carry will occur, right? This is one case where carry can be generated. Okay. So in that case, when you will add 1 1, so S7 will be 0, right? And there will be one carry C7 will have one carry, that will be 1. In that case, C6 can be 0, maybe, right? It can be 0 or it can be 1. In that case, what will condition we will get? C7 or just here we are assuming that C6 will be 0 only. Okay, so C7 and C6 dash, there is one case, this one is one case. Okay, let's see, we can say equation number 1. Okay, so the another case can be happen if both A7 or B7 can be a 0 or 0 1 or 1 0, right? So in that case S7 will be 1. Okay, if C6 have carry, that means C6 have 1, that is propagated to 1, and A7 B7 will be 0. Here we are assuming in order to make the condition. Okay, so if A7 and B7 will be 0 and C6 have a carry, C6 can be 1. So in that case, what will be the condition? That means C7 dash C6, only because C6 is 1 and C7 is 0. Okay, let's see, this is equation number 2. So if we combine these two equations, so what will we get? C7 C6 dash plus C7 C6, right? Because in the last digit only we can get the carry. Okay, in from last digit the overflow can be occur. Okay, so these two we need to take care. So in order to make, or in order to detect the overflow, this is this C6. So the condition of the overflow will occur can be, so first condition is A7 and B7 is 1. So that means A7, B7, and when A7, B7 is 1, so S7 we will get 0, right? A7, A6, sorry, B7, both are 1. If we add these two, so S7 will be 0 and 1 carry will be propagated, then overflow will occur. Okay, so that means S7 dash will be there, right? In this case, the other situation is if A7 and B7 both are 0, right? And C6 the carry is 1. So in that case, we can write it A7 dash B7 dash S7, right? Because the carry of C6 will be added. S7 B7 is 0 0 0 0, but carry from the C6 will make it 1. So if these two is 1, then overflow will occur. Not in that case, all the carry bits C7 to C0 are 1. Not in that case also, the carry bit C7 is 1. So if C7 is 1, so in any case if both are 0, so then will be 1 only. So in that case also not, so option C is the only correct option. And overflow is said to have occurred if this condition will be there. Okay, so have you understand this question? So option C is the only correct option for this question. And overflow is said to have occurred if A7 B7 into S7 dash plus A7 dash B7 dash into S7 is 1. In that case, overflow will occur. Okay. So I hope what is meant by overflow. If you are adding two numbers and that two numbers is giving an extra carry, already I have given one example. So have you listened? Did your question is clear? For example, if any circuit have only 4-bit storing capacity, right? And for example, 0, 1, 1, 0, 1, 1 again 0, 1 carry 1, 1, 0. So there is a one extra bit, so that is called overflow. Okay. Overflow is a condition that indicates results is too large or too small to fit into a original data type. Let's say there is 8-bit data type. So if there is a carry generated and that cannot be stored in the data type, so in that case overflow occurs. Okay, that does not fit into a data type. This is the overflow. Okay, so I hope all of you understand this question. So moving to the next question. So next question is the minimum number of 2 input NAND gates are required to realize a half adder. So how many NAND gates are required to realize a half adder? So can anyone tell me what is a Boolean expression for sum and carry of adder, half adder? So Boolean expression for sum of half adder is x XOR y, right? This is a Boolean expression of half adder. Yeah. And what is a carry generated by half adder? Right. AB or XY. You can say here I am taking the XY as an input. So here I am writing XY. Okay. So how many NAND gates are required to two input NAND gates are required to realize the half adder? So this can also be written as already you know that x XOR y, x dash y plus x y dash, right? So let's try to realize using the AND gate, NAND gate. X and y. So what we will get here? X y bar, right? Now what we can do, we are giving one input to x and one input is connected to the next two NAND gates to xy bar, and one is x from x and another one is from y. Okay, so what we will get here? X into x y bar, and similarly what we will get here? Y into x y dash and dash. Now it is going to give next NAND gate, then maybe some will be there. So let's solve this one first. I'm removing it from here so that we can solve it. So from here x into, if you remove this dash, then you will get xy, here double dash, here x dash, right? So you will get x dash plus xy here, right? In this, similarly, it is equal to y dash plus xy, right? Now these two inputs I have given to another NAND gate, so x dash plus xy in one bracket, these are in multiplication, then y dash plus xy dash. So now let's solve this. X dash plus xy dash plus y dash plus xy, right? Now again further if you solve it, you will get x double dash, I just am removing x double dash will be there and multiplication with xy dash, right? Plus here y double dash into xy dash. Here you will get x, if you further do this in this, x dash plus y dash, right? And solving it, if we are multiplying it, x dash and x plus, so x dash will be 0, so x y dash we will get from here, and similarly in the next we will get y x dash plus y dash. Similarly y x dash will be there and y dash will be cancelled out. Okay, so what we have got x XOR y here. So what we have got here, x XOR y, which is a sum of Boolean expression or sum. Now what we need to solve for carry, right? So I am removing it from here so that we can solve it. So now already for carry we have expression only xy, right? So here we have got the xy bar. If we are giving these to an AND gate, another AND gate, then we will get a carry, that is x y. Here the both the inputs have been sorted. Okay, so how many NAND gates are required to realize a half adder? That means the NAND gate number 1, 2, 3, 4 and 5. So total 5 NAND gates are required to realize a half adder. Okay, so I hope all of you have got this. So moving to the next question. So next question is, for a logic family, given that VOH is the minimum output high level voltage, VOL is the maximum output low level voltage, and VIH is the minimum acceptable input high level voltage, and VIL is the maximum acceptable input low level voltage. So the correct relationship is, which one is the correct relationship between these options? So let's first see that already you have seen in this video lecture the diagram input output voltage range. So from I am making that diagram so that you can understand it better. So let's it output voltage range or input voltage range, anything. Okay, so there is a high voltage, high level voltage or low level voltage. Let's say it is a input voltage range, input, and this one is a output, right? So if the input voltage for high level is allowed, so what is, we can see VIH means high level of input voltage. Similarly, if L is there, that is input voltage of low level, right? VIL, right? This is the one is maximum acceptable range, and this is the output range. Let's so always output will accept this lesser than the input voltage because of some noise or corruption in the signal. Let's see, this is the high level voltage of the output. O represents the output voltage and here I represent the input voltage. This is a high, H represents the high level and this L represents the low level. Okay. Similarly, for L also, L we need to make it little bit down. So what is it? VOL, right? So let's, in order to make a comparison, let's try to make it like this so that we can. So from the figure, we can find out the which one is the highest voltage level. That is for high level VOH, right? Then VIH. Then which one? From the figure you can tell this is input voltage at low level VIL, then VOL is the lowest. Okay, so from this diagram already you have seen in the video lectures, from there we can make this relation. Okay, for a logic family, given that these are the input and output voltage, maximum minimum input and output voltages at for input and output circuits. So we need to find out the correct relationship. So from the options we can see that which represent the correct relationship. Option B is matching with this, so option B is the correct. VOH, then VIH, then VIL, then VOL. Okay, option B is the correct answer for this question. Okay, so I hope all of you have got this question. So moving to the next one. Question. So next question is based on this only. A logic gate noise margin parameters are given. That means VIH, input high voltage level, out input voltage at low level, output voltage at high level, and output voltage at low level is given. Then identify the value of noise margin high and noise margin low respectively. So noise margin high represented by NMH. So noise margin high, how we can get it? So already you have seen in the previous video, noise margin of high is the difference between these two, because this is the output minus input noise margin we need to find out. So noise margin high, the formula is, yeah, VOH minus VIH, right? VOH minus VIH, right? So here already is given what is it? VOH value, that is 1.8 volt minus VIH. What is the value of VIH? 1.5 volt. So what we will get? 0.3 volt for noise margin at high level. Now we need to find out noise margin at low level. So again, from that previous figure, the formula can be written as VIL minus VOL, right? So how here we are writing the first low input low level, then output low level. So from here we can see that the input low level is greater than the output low level. That's why we are writing. Otherwise, we will get a negative. So what is a input VIL is 0.2 volt minus what is the VOL 0.1 volt. What we will get here? 0.1 volt. So noise margin at high level is 0.3 volt and noise margin at low level is 0.1 volt. So let's see in the options which one is correct. That is option C, 0.3 volt and 0.1 volt. Option C is the correct option. So this is a formula for noise margin, high level and noise margin at low level. Okay, this is a output. This one is represent the I represent the input, O represent the output. VOH and VIH. Okay. Okay. So I hope you are understanding. Moving to the next question. So next question is the minimum number of two input NAND gates are required to realize a full adder. Now we need to realize a full adder using two input NAND gates. So how many NAND gates are required to realizing the two input to full adder? Already we know that for realizing the half adder we require a 5 NAND gates. So for realizing the full adder, how many NAND gates are required? Can anyone tell me? Okay, so let's first see that what is a Boolean expression for sum and carry of a full adder. What will be the Boolean expression? Let's sum is x XOR y XOR z, right? I hope in the video lectures already it is already told about this. And what is a carry expression for a full adder? No, not 10. Let's make it and then check it whether it is 10 or less than that. Okay. So from that the carry will be xy plus yz or zx. In order to make it NAND gate, the other expression for carry is also there. That is xy plus x XOR y if you simplify this one. This is a Boolean expression for sum and carry. Okay. So let's make it. I am moving it here so that because we need lot of space here. Okay. So first NAND gate. So here we are giving. And can you tell me normal how we can make some expression the normal just taking two XOR gates, right? Here x y and then giving to the next XOR gate. This one is z. So x XOR y. Here we will get x XOR y XOR get, that is sum. And for carry we need to require x XOR y one OR gate only. Okay, AND gate and OR gate to represent the carry. So already we know that. So for first XOR gate, first we need the 4 NAND gates. So here x and this one is y x1 to the from here x and another to the and here we will get xy dash, right? Here we will also get, already we know that here x, here xy dash, so x into xy dash dash. Similarly here y, we are getting at this input and another input into xy dash dash, right? If you solve it here, we will get x XOR y. Already we have solved it. If you solve it, you will get the x XOR y. Okay. Now we need to give it to the another NAND gate because we need a one more XOR, right? And for this we are giving here z. So x XOR y into z dash, right? We will get at this input. Now again we need to give it to the another NAND gate, these two. Here, so this input is going x XOR y into z, but to one of the input of these two, and the another z is going to this, and x XOR y will go to this, right? So here you will get x XOR y, x XOR y. We need to solve it into z bar in one bracket into z to the other bracket to other, right? And similarly in this one, from here you will get the some expression. In this you will get, in this output you will get the x XOR y in one bracket, right, into x XOR y into z dash into dash. Okay, here you will get, and here we will get this one x XOR y into z dash into z overall dash. And if you give to the another NAND gate, you will get x XOR y XOR get. If you further solve the solution is very large, so if we are going to solve it here, so it will take a lot of time. If you solve it, you will get it. Otherwise, if you have any doubt, you can ask in the next class. First try to solve it and let's see. Okay. Now for carry, I am taking the another NAND gate here. I am representing it as a carry. So for one input is x y bar and another we will get from here for carry. So what is the input here? X XOR y into z dash, and here we are getting x y bar. So if you take it, you will get xy dash in multiplication with x XOR y into z dash whole dash, right? And if you remove that one, you will get xy double dash plus x XOR y into z, again here double dash, right? double dash will be cancelled out. You will get here xy plus x XOR y into z, which is the expression for carry. Here it is written. So from carry you will get, and for this we need to solve it a lot. So you can solve it at your home and we'll see you will get the x XOR y XOR z. So total number of NAND gates are required to realize a full adder is 1, 2, 3, 4, 5, 6, 7, 8, 9. So total only 9 NAND gates are required to realize a full adder. Okay, that is option C will be the correct option for this case. Okay. Okay, I hope, are you getting, are you understanding, or should I explain it again? So just we need to make first or start from basic. So how XOR gate is making using the two input NAND gate. For making one XOR gate, there is 4 NAND gates are required. This is a basic structure for NAND gate. For another XOR gate, we require the another structure. Okay, so you will get x XOR y XOR z from here, and for carry only one, because from we are taking the inputs already solved NAND gate, so that's why here it is a only one NAND gates in addition required for carry output. Okay, so total 9 NAND gates are required for full adder, to realize a full adder. Okay, so I hope all of you are getting. So moving to the next question. So in a half substructure circuit with X and Y as input, the borrow is represented by M and difference is represented by N, are given by. Okay, so let's see the what is a half substructure circuit. So already we know it is same for half adder. So let's see first from the truth table of the half substructure to input. So there are two input X and Y, and there is a difference. Difference is represented by N, and borrow is represented here by M, right? So what are the input combination? That is 0 0, 0 1, 1 0, and 1 1. Okay, so N is difference. 0 minus 0 will be 0 only. There is a no borrow will be there. And 0 minus 1. So from 0 we can't take difference from 0 minus 1. So there will be 1, and there is a 1 borrow will be there because we are taking from the next gate. Okay, so 1 0. So 1 minus 0 will be the 1, and there is a no borrow we have taken. 1 minus 1 will be 0, and there is a no borrow will be there. So now from here we can see that this is a truth table of a half subtractor. So let's see the difference. What is a Boolean expression for difference? So we can see that the difference is a normally XOR gate. Okay, X XOR Y means 0 1 plus X Y Y. It is a XOR representation of X XOR Y, right? Now for borrow, what is the expression for borrow? It is 1 at 0 1 only, so X dash Y, right? So from the truth table we can see that the difference is X XOR Y and borrow is X dash Y. So which option is correct? From the options we can see that X XOR Y, only option C is the correct option. And also the circuit diagram representation is for half substructure is xy, that is x XOR y. This is a difference. And for borrow, this is x dash, means we need to take a NOT gate so that we can get x dash here, then y. Here we will get x dash y. This is a circuit representation or logic gate representation of half substructure, and these are the expression for half substructure, difference and borrow, x XOR y and x dash y. Okay. Okay, I hope you are getting. So moving to the next question. So next question is, if the output of a digital circuit makes a momentary transition to logic 1, okay, while otherwise the output is logic 0, means output at logic, let's see, it is a logic 0 and this one is logic 1. So it is said that if the output of a digital circuit makes a momentary transition, so at this moment let's take, see, it can be 1, and while otherwise it is out 0. Okay, so it is called a static 1 hazard or static 0 hazard or dynamic hazard or no hazard. So what will be it is called? So if the output of any digital circuit is at logic 0 only and it takes momentary transition at logic 1, so it is called static 0 hazard. It is called static 0 hazard. And if output of any digital circuit it is at logic 1 and make a momentary transition at logic 0, then it is called a static 1 hazard. Okay, static 1. And dynamic hazard is if continuous transition will be there at logic 1 to 0, 0 to 1, then it is called a dynamic hazard. Dynamic hazard. So option B is the correct answer. It is a static 0 hazard. Okay. So moving to the next question. So a full adder can be realized using one half adder, two NAND gates, two half adder or one OR gate, two half adder, one AND gate, or two half adder, two NAND gates. So can anyone of you answer this question? A full adder can be realized by from the following options. So already we know that what is the logic expression or Boolean expression for full adder. For sum, we know that is x XOR y XOR z, and for carry it is xy plus yz or zx. There is one other expression is there also, xy plus x XOR y into z. So there, if we add the two half adders, here we are giving the x and y, here is the sum and carry, sum and carry, right? And if we connect it to other, one is to the other input and another one is, already we know that what is it. So we need two half adder, here it is z, here the input output of the another sum, and thus this one is carry out if we, and here is a sum or carry. So from here we will get the total sum. Here it is, can we take S1 or C1? Yes, C, overall carry. And if we add these two, we will get the overall carry. So 2 half adder and 1 OR gate are required to realize a full adder. So option B is the correct answer for this question. Okay. Yes, 2 half adder, 1 OR gate are required. So moving to the next question. So next question is, which logic function is implemented by the CMOS complex logic structure shown in the figure? So from the figure, it is a CMOS structure. So it is called the upper half is called pull-up network, right? And pull-up network is made by a PMOS transistors, right? And in the lower one, pull-up network. And the lower one is called pull-down network. This one, pull down. Just pull down network, and this is made by a NMOS. Okay, so NMOS and PMOS both are connected in opposite. So from any of them, either pull up or pull down, you can make a logic function. So here we can see that A, B are in series. Okay, this is the N type NMOS transistor. So just A, B in series. So A or B, A into B. And this AB in series is connected with C in parallel, right? So there will be a plus, and output there is in a complemented form. So overall expression for this network, you will get the A, B plus C bar, and you are calculating for the from the pull-up network. So you will get what? Here A and B are connected in parallel, so that means A plus B and C, right? So this is a P type, so there will be a bar. So if you expand it, you will get the same answer. So A bar plus B bar into C bar. Okay. So output, let's see in which form. This is AB plus C dash. Option D is the correct answer. So you can calculate from anywhere. If you further solve it, here you will also get AB plus C dash only. Okay, from any either pull-up network or pull-down network. Okay, so AB plus C bar is the answer. This is basic structure of the CMOS. In the upper side, this is the P type MOS structure, and then the pull, that is called pull-up network, and the lower one is connected to a NMOS transistor, that is called the pull-down network. Okay. So moving to the next question. So the next question is, consider the circuit shown below. Which of the following statement correctly describe the output X? So which of the following statements describe the expression X? So from the figure we can see that there is a 4 full adders are connected in a series, and there is one S is given to one is direct. Every full adder has direct connection with the one input, and another the XOR connection of with B3, and there is one variable is called S. So S, it is a adder or subtraction circuit. Okay, if S is equal to 0, then it will act as an adder. If s is equal to 1, it will act as a subtractor. Okay, you can check it. If s is equal to 0, so 0 XOR b3, what you will get? b3 only, right? b3 or b3 only. Okay, so a3 b3 will add the and will get the sum. And if it is 1, then it will act as a subtractor. Okay, so let's check for x. What is the expression for x? It is a XOR of C4 and C3, right? From here we can see that, or we can write it C3 C4 dash plus C3 dash C4. Okay, so already we have solved that to occur a overflow condition, that will be 1 only. If these with the 1 is 1, then overflow condition will occur. Okay, so let's go through the options, then we are able to make it. So x is generated carry out bit. No, x is not generated a carry out bit. Carry out bit is C4. Okay. The next option is x is equal to logic 1 when addition is performed, and x is equal to logic 0 when subtraction is done. So x is logic 1 when addition is performed, and x is equal to logic 0 when subtraction is performed. So let's check it. So if s is equal to 0, then we have told that addition will be performed. So a3 b3 given to the adder, and output is represented by f3, right? So this can be we have to calculate it, but more, otherwise no. It is only x is equal to logic 1 when addition is performed, no c3 XOR c4, and in both the cases it will, this operation will be only performed, c4 XOR with c3. Okay, whether it is addition or it is subtraction, in both the cases, because circuit is same. So this is also not done. So x is equal to 1 if there is an overflow during either addition or subtraction. Option D is x is equal to logic 0 if there is an overflow during either addition or subtraction. But before we have already told in the previous slide is overflow is, what is the overflow condition to occur? If the carry, the last two bits will be in XOR, and that can be equal to 1. So option C is the only correct option in that case. Okay. If x is logic 0, there is a no overflow will be either during addition or subtraction. So only possible option is option C is the correct. Okay, in that case. In any case, whether addition, you need to perform either addition or subtraction, the logic will be 1 for overflow to occur. Okay. Okay, moving to the next question. The product term to be included to remove possible static hazard for a function wx plus w dash y dash. So which of the following product term must be included to remove the possible static hazard? So let's check that. The function is given wx plus w dash y dash, right? So let's first check that whether it is a sum of product form or product of sum form. So from the function we can say that this is a SOP form, right? So SOP form is for what? For static 1 hazard. Already told in the lecture. So SOP is represented for static 1 hazard. Okay. So let's make a K-map so that we can see that of the following. Yes, anyone want to say something? Okay, so let's make a K-map for this. Then we are able to see which of the following option will be included in order to remove the static hazard. Static, which static? Here it is given in a sum of product form. Okay, that means sum of product form related to the static 1 hazard. If there is a product of some form, then static 0, that one is written for static 0 hazard. Okay, so W, X and Y. I am taking this side XY and this side W. 0, 1, 0, 0, 0, 1, 1, 1, 1, 0. So first we need to write WX. So let's see in which column from which these rows and column we will get the WX only. So WX, so W means 1 only. If we are taking this one, then W bar will be. So W and X. So if we take X, this represents the X, right? So from here we will get WX expression, right? Now W bar, Y bar. So in this row we will get the W bar, and Y bar from where we will get? That means 0 must be a common in the next this side. This is X, Y, this one is X. Okay, so Y from this and from this from and this we will get the, if we make a grouping like this, you will get the W bar, Y bar, and if you make the group like this, you will get the WX, right? Okay. So which of the following product term must be included to remove the possible static hazard for the function? So from the K-map, we can see that the possible pair can be made from this one, right? In order to remove, so if we move from this one to this one, there will be no static hazard. So let's see. So there is no W will be cancelled out if we make grouping like this. So what will be the X, Y bar, the possible pair that will be included in this term, so that will possible remove the static hazard. Okay, so X, Y bar must be included in this function, so that will remove the static hazard. Okay, option B is the correct answer for this. Okay, are you getting these questions? Are you getting? Okay. See how to remove the possible static 1 or static 0 hazard. So if static 0 hazard, then the product of some form will be there. Here it is a sum of product form. So that means the static 1 hazard will be there. Okay. Okay. So the next question is, which of the following is not a property of a CMOS logic gate? Option A is high switching speed, option B is low static power consumption, and option C is high packet density, and option D is high noise margin. So if you have gone through the properties of CMOS logic gates, so CMOS logic gates has a properties of high noise margin, no static, very less static power, and comparable rise and fall times, and highly compact in structure. So these are that means high packaging density is the property of the CMOS. High noise margin is also property and low static power. It can very, that's why it is very famous, because it consumes very less power. But already we know that the CMOS circuit is made by both, right? NMOS and CMOS, NMOS or PMOS, pull up network and pull down network. So while it takes taking in the performance, the switching speed is comparable high to other logic gates. And also there is a voltage current relationship in the MOS transistor is in this form, right? Already we know that what is a voltage and current relationship for MOS. So there is a COX, right? W by L VGS minus VT into VDS minus VDS whole square. This is a voltage contribution of a MOS transistor. So that is applicable for both PMOS and NMOS. So that will take the high switching speed, or also it takes two transistors, NMOS and PMOS. The upper side is PMOS and the lower side is connected to the NMOS, right? So that is the reason for the high switching speed for the CMOS logic gate. So high switching speed is not a property of a CMOS logic circuit. So option A is the correct answer for this question. Okay. Okay. So I hope all of you getting. So moving to the next question. So next question is the number 0010 11110 when converted to BCD, then what is the BCD conversion of this number? So how you are going to convert it? So firstly, what is the decimal equivalent of this number? What will be the decimal equivalent of this number? Can anyone tell me? Just try to give answer at least for this question. So the number is 001 0 111 0, right? So how we are going to convert it into decimal? What will be the decimal equivalent of this number? Can anyone tell me? Yeah, right, 46. So to convert into a decimal, so already we know that we have to take a 2 to the power in this 3, 4, 5, 6, 7. So first one is 2 to the power 5. That means 2 to the power 5 means 32. Right, multiplied positive powers of 2, right, 5. Then you will get from here 32. This is 32 plus here at which place 2 to the power 3, wherever it is 1, then we will take, otherwise in that all these cases it will be 0, so I am taking only 2 to the power 3 is 8, right? And then again 2 to the power 2, that means 4, and 2 to the power 1 is 2 only. If you add all those things, you will get 46. So decimal representation of this number is 46. Now we need to convert it BCD. BCD means binary coded decimal. So binary coded decimal number is only, it is going to 0 to 9 only. After 9 it will 9 to 15, it will act as a don't care condition. Okay. So BCD representation of BCD is represented only 0 to 9 numbers, not other numbers. So and it is same as a binary representation till 0 to 9. So what is a binary representation of 4? Can anyone tell me? 8421, that one. That is 0 1 0 0, right? Yeah, someone else. Yeah, right. And what will be for 6? Already we know that 8, 4, 2, 6, so 4. And for 6, that is 0, 1, 1, 0. Okay, this is a BCD representation. BCD representation of this number. So let's say 0, 1, 0, 0. Option A is the correct answer. Okay, 0, 1, 0, 0, 0, 1, 1, 0. So the BCD representation of this number is 0, 1, 0, 0, 0, 1, 1, 0. Okay, you're correct. Okay, so moving to the next question. So next question is, the output of logic circuit given below represents which gate this logic circuit represents. So for this, we need to find out what will be the logic expression for this. So I am just writing it here in order to make other circuit and then calculate it. So what will we get for this? What is this gate is NOR gate, right? So what we will get there, both inputs are sorted. So NOR gate representation is A plus B bar if the two inputs are there, right? This is a NOR gate. A, B. The output of NOR gate A plus B bar. So if both the inputs are sorted, only A is there, we will get A plus A bar. So A only, right? A bar only. So here we will get A bar, and similarly in this we will get B bar, right? Now if we add these two, here we will get A bar plus B bar whole bar, right? And again we are going these two put the inputs of another NAND gate. So here we will get A bar plus B bar whole bar whole bar, and these two bars will be cancelled out. So we will get A bar plus B bar, and it also can be represented by A into B bar, right? That can be represented. Okay, so which gate it is representing the output of this logic circuit? This is a NAND gate representation, right? So option 4 is the correct answer for this. Yeah, NAND gate representation. The circuit, the output of this logic circuit is representing the NAND gate. Okay. Okay. So moving to the next question. So the next question is, what will be the fundamental frequency of the following circuit if inverter delay is 100 nanosecond? Okay. So the inverter delay is 100 nanosecond. That means this is called inverter, already you know that. And when it is passing the input to output, there is a 100 nanosecond delay will be introduced. Okay. So already we know that the fundamental frequency is representing by f, and it is 1 by t. T means time period, right? And the fundamental frequency is inversely proportional to time period, right? Already we know that. Okay. So so in that case, in the digital circuit, if that type of question is there, then T we will get by this formula to get the time period of this feedback type NAND multiple NOT gate is connected in the feedback loop, then we will find out by this formula 2n TPD, where TPD is the propagation delay or gate delay, or you can say that gate delay. And here gate delay is given, here inverter is the gate, so gate delay is given here 100 nanosecond. That means TPD is 100 nanosecond. N is the total number of logic gates. Number of logic gates. And TPD is the gate delay. Gate delay or propagation delay. Okay. And 2 is multiplied because the logic gates are connected in a feedback form. Okay. So first we need to find out the T. So 2 is 2. Number of gates are 3, right? And TPD is given is 100 nanosecond. So 100 into 10 to the power minus 9, right? Nanosecond is represented by minus 9. Okay. Now it will come 6 into 10 to the power minus 7, because here it is 100 to 10 to the power 2 minus 9 to minus 7 will be there. Okay. So TPD is this second, right? We will get. Now we need to find out the fundamental frequency. So 1 upon T, right? So 1 upon 6 into 10 to the power minus 7, right? Now it will it will go up to 10 to the power 7 divided by 6. Okay, if you multiply it, you will get 1.67 or 660 into 10 to the power 6. Okay, because 10 to the power 7 will be there, so if we will take 10 into 10 to the power 6 divided by 6. If we divide 10 by 6, you will get 1.67 into 10 to the power 6, and it can be said 1.67 megahertz, right? 10 to the power 6 is called megahertz, right? Already we know that. Yeah. And if you, it's not minus 7, it will be plus 7. If it will go up, so plus minus will be plus, right? So 1.67 megahertz. It is megahertz. So option 4 is the correct option in this case. Yeah. And if you multiply by 10, 1.67 into 10 to the power 6, and 10 to the power 6 is called megahertz. Okay. So 1.67 megahertz. Option 4 is the correct answer for this question. Okay. So have you got this question? I hope all of you have got this question. So moving to the next question. Okay. So next question is also related to the CMOS inverter or CMOS logic gate. So question is, the logic function f of xy here is realized by a given circuit. Which logic function is realized by the given circuit? So let's see. Here it is given the up. Here we first divide which one is pull. This one is pull up network and this is pull down network. Okay, pull down network, pull up network. First see which one is P type MOS. This one is overall P type representation, and this is NMOS. So calculate common. So let's see. The input is here x dash, right? And here y dash, and here it is directly x, and it is also connected directly y. Okay, so fxy comma y will be, so these two connected in series, x dash and y dash, and this two also is connected in series, and these two then connected to the parallelly. Okay, so x dash y dash, it is in series, so multiply, and these two connected to the parallelly, that means plus, to these two series circuit, series and most. So x and y whole bar, right? Correct. Now further solve it. X dash y dash, if we remove this bar, so this will be whole bar multiplied by x y bar, right? Now again further if we solve it, we will get x double dash plus y double dash into x dash plus y dash, right? So we will get here x, only x, double dash will be cancelled, x plus y in one bracket, and x dash plus y dash in the another bracket, right? Now multiply these two, x into x dash plus x into y dash, then y into x dash plus y into y dash. X dash y dash will be 0, right? This will be cancelled out. Then what we will get? X y dash plus y x dash, and it is, what is this? This is the XOR of x XOR y, right? Okay, so it is a XOR, it is realizing the XOR gate. So option 4 is the correct option. Okay, so have you got this? I think all of you have got this, already solved it. Okay, so moving to the next question. So next question is, during the design of BCD to 7 segment decoder, what value is initialized to display 9? So during the design of BCD to 7 segment display or decoder, it is a 7 segment decoder. So let's first see what is it. Block diagram of BCD to 7 segment display decoder. So BCD, how many bits are represented in the BCD? So it is represented by 0 to 9. So 0 to 9, that means 0 0 0 0 to 0 1 0 0 1, right? 9, that means 8 plus 1 9, right? 0 0 to 1 0 0 1, right? So there must be 4 inputs, right? That means A, B, C, D. Let's see, inputs are A, B, C, D, and it is also A, B, C, D. And 7 segment display, that means the 7 segment display means 7 outputs will be there. So already we know that what is the 7 segment display. There is one display like this, right, which is used to display the bits. If there is, there are some representation, it is called A, this line is called A, then it is B, then C, it is called D, and this one is E, and this one is F, and this line is represented by G. So if we want to represent a 0, then how we can? Only A, B, C, D, E, F will be light up, and this G will be off. So it will represent the 0. If we want to represent the 1, it is a for 0 bit representation if we want to, and it will represent decimal representation. Okay, 7 segment. If we want to represent 1, then what are the bits which will be on? That is B and C. If we want to display 2, then what are the alphabetical order? To be 1 and other will be, so for 2, what are the symbols? No, it will for 2. So if we light up 2, then it will be the A will be on, B it is G, and it is E, and this one is D. So these will be 1 and all other will be off. So this is a 7 segment display. This is called 7 segment display. Okay, already I think you have studied all those things. Just I am telling for the basic purpose. So here what we want to display, what will value is initialized to display 9, which value we need to display, and this is given in hexadecimal form, these values, right? From the options we can see. So to display 9, which are the alphabetical things, so that should be turned on. That means this one, this one, this one, and this one, and again this one, this one. So what are the A, B, C, D, F, and G? If these are on, then it will represent the 9, right? So here it is representing like this: A, then B, C, D, E, F, G. Here are 7. So it is BCD. Let's say BCD to 7 segment display. It is 7 BCD to 7 segment display converter. Okay. So let's check. So A, B, C, D, E, F, G till G will be there. It is D. A, B, C, D, E, F, G. Okay. So what are the values will be 1, so that we can able to display 9. So A will be 1, B will be also 1, right? And C is also 1, D is also 1, E will be 0, F will be 1, and G is also 1 to display the value 9. Okay, so from here we can directly convert it into a hexadecimal, because it is already asked only the hexadecimal representation. Okay, so make a group of 4. Already before we have done that. So what is the representation? It is a 7, and this one is 8, 4, 2, 1. So 8, and this is 2, 10, 1, 11. What is the 11? 11 is represented by B. So 7B in hexadecimal. Are you getting these questions? Okay, 4 you are getting a thumbs up. Okay, option 4 is correct. 7B is the hexadecimal representation of to display value 9. Okay. Okay. So moving to the next question. So next question is, let the input of a subtractor is A and B. We want to write A, B, C in same order. In which related to which question? We want to write A, B, C in same order. That is one related to BCD to 7 segment display. This one. Okay, we want to write A, B, C in same order. No, it is like this. It is a representation of a 7 segment decoder A, B, C in this order. Here it is A, B, C, D, then E, F, and this one is representing the G. Okay, so we have to move in this direction only. This one is A, B, C, D, E, F, and this one is G. So whatever number we want to represent, and 7 segment decoder display the decimal digit. Okay, so here decimal digit is 9. So 9 is represented by these two. How we can display the 9? By these. So A, B, C. So we have to write in this order only. Here output is also A, B, C, D, E, F, G, H. Okay. Are you getting? Yeah. Okay. So moving to the next question. Let the input of a subtractor is A and B. Okay. Let the input of subtractor. Subtractor is represented, what is it? A XOR B. Here A, B is only given, two inputs are only given. So it is half subtractor. Okay, right? And the carry is half subtractor A bar B, right? So here it is given what the output will be if A is equal to B. If A is equal to B, what will be the output? So let's see for some. A XOR B is A bar B plus A B bar. If A is equal to B, so here what we will get? A is equal to B. So in place of A there is B. So B bar and B bar. So that will be the cancel out. That output will be 0. For carry also A bar B is given. So A is equal to B. So B bar B, in that case, in case of carry, their output is also 0. So let the input subtractor of is A and B, then output of will be, if the output will be 0. Okay. Option A is the correct answer. If A is equal to B, then subtractor both output sum and carry will be 0 only. Okay. Okay. So I hope all of you getting this question. So moving to the next question. So next question is, the circuit shown in the figure represents the circuit. Here it is XOR gate, right? So it is A XOR B. Here A XOR B XOR C, and output is A XOR B XOR C XOR D, right? F is equal to. So it is a even parity generator, odd parity generator, odd parity checker, or odd parity generator, even parity checker. First of all, this is a circuit. So it is not checking. It can be checked, but here it is a generator only. Okay. So this one is a even. So how we can check it, whether it is a even parity generator or odd parity generator? So 4 inputs are there. Okay. A, B, C, T. So the combination can, what are the combination for this? 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1 for 3, 0, 1, 0, 0, 0, 1, 0, 1 till 15, right? 1, 1, 1, 1. Now F, A, B, C, D. So let's, it is all XOR. So first XOR A and B. A 0 XOR 0 will be 0 only. Let's go with the 0, 1, 1, 0, 1, 1. What is the A XOR B? Here XOR gate 0, 0. Already we know that truth table of XOR gate. Inputs are same, then output will be 0. Inputs are different, then output will be 1. So all are same, so output will be 0. And here 1 is different, so output will be 1. Here also 1. Here 0 XOR 0 will be 0, 0 XOR 1, will be 1, 1 XOR 1 will be 0. Okay, so here 1, here 2 inputs are 0, 2 output inputs are 1, so at the end it will come 0. So like this it will come. So from this table we can say that when the either 0 the are in even the when the ones are even, then output will be 0. When the ones are odd, then output will be 1. Okay, so even parity generator, the output is 0 when even number of ones. For even parity generator, it is a you can say it is a definition. For even parity generator, the output is 0 when even number of ones are there. And similarly for odd parity generator, the output is 0 when there are odd number of ones. For odd, if there is a odd number, only C is there, in that case the output will be different. Okay, here it will be 0, then here it will also 0, then here will be 1. Okay, so it is a even parity generator circuit. Okay, because even number of function, or you can say that inputs are XORed, so it is a even parity generator circuit. Okay, next one is which of the following function reflects the odd parity generator. Okay, so already told you, for odd parity generator the output is 0 when there are odd number of ones in the given bits. So here it is a only 3-bit representation is there in all the options. So here we will take only 3 bits. So let's see what will be the function for odd parity generator. So let's see, the inputs are A, B and C. The output is F, right? Then make all the combinations 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0 and triple 1. Okay, now it is an odd parity generator. Okay, so if ones are in odd, then output will be 0. So sorry, here it is 1, there are no ones. So when the ones are in odd, then output will be the 0. Here it is also 0. Here 2 ones are there, so it will 1. Here it is also 0. Here it is 1, 1. Here it is 0. Okay. So now we need to make a K-map in order to find out, or we can directly, not required for K-map. So what will be the function if we want to represent in the min terms? What are the values we will get? Where ones are there, that we need to write it. Okay, the min term representation of this, which is 0, at which position? 3. Here it is which position? 5 and 7. Okay, 5 and 6.
6.
Yeah, it's 6. It is 6. Okay, this is the min term representation. Now if we want to write in a Boolean expression, so at which term it is 1. So first one is A dash, B dash, C dash, right? Now next one is at 3. So A dash, B, C. Next one is A, B dash, C. Now next one is A, B, C dash, right? Now take a common. Here it is A bar will be common. So B dash, C dash plus B and C. Again, if we are taking here, A is common in both. So A, B dash, C plus B C dash. Okay, right? Now, what are the representation? A dash, it can be represented by, already it is a XNOR gate representation, already we know that. Here, A, it is a XOR representation of B and C. Yeah, okay. So let's take this term is X, okay, for in order to solve. So already we know that in XOR representation, any term, okay, it can be represented by like this, B XOR C. If there is a bar in any one or both, then it can be represented B nor C, right? Already we know that that is equal. So if we see that it is what this representation A bar X and A, this if we take X, if we take the bar, then it is a, let's say B nor C plus A. It can be represented by B nor C dash, right? If you further solve it, you will get the B XOR C only. So it is what representation it is? A bar X, if we take it is X, and A into X bar, that means it is a XOR representation of these two. So that can be represented by A XOR B C, right? Have you understand this one? So odd parity, and this is the one is the final answer. So let's see. A XOR B in brackets B nor C. Option 3 is the correct answer. If you see this or solve it. Okay. Have you got this at this point? If you further solve it, you will get. Okay. So I hope all of you have got this. So option 3 is the correct answer. Okay. So option 3 reflects the odd parity generator A XOR B, A XOR in bracket B not C, B XOR C. Okay. Okay. So moving to the next question. So next question is the minimum function that can detect the divisible by 3 8421 BCD code digit represented by D8, D4, D2, D1 is given by. So divisible by 3 only we want to find it out. Okay. So it is a BCD code digit. So only 0 to 9 till 0 to 9 we have representation, and 9 to 15 there is a don't care condition. Okay. So first we need to make a truth table. So I am making it here, then I will remove that truth table in order to, because we need a space. So minimum function that can we get to detect divisible by 3 we need to find out. So here it is already given in the D8, D4, D2, D1 form. So we need to write it. Okay. D8, D4, D2, D1. This one is 8. Okay. Then let's see output is F. Okay. So we need to write 0, 0, 0, 0. Sorry, 0 is one extra 0 will be there. 0, 0, 0 and 0. Okay. And 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1, 0, 1, 0, 0, 0, 1, 0, 1, 5, then 6, 0, 1, 0, 0, 0, 0, 1, 0, 0, 1. So, and all other places there is a don't care condition till 15. So I am not writing it here. Okay. So now we have to find out divisible by 3. So 3 is divided by which? So 0 can be divided. So it will be the output will be 1. 1 is not divided by 3. Output will be the 0. Output will be the 3 will be divided by will be 3. So it will be 1. 369 at 369 it will be. So divisible by 3 we need to find out at the place of 369 it will be 1 and all other places will be the 0 only. So 0, 0 and it is 6. So it is divisible by 3 and it is also 0. 8 is also 0 and at 9 it is 1. So this one is a truth table for divisible by 3 in order to find out the minimum function. Now, in order to find out these functions, so we need to make a K-map already. Okay. So here this side I am taking D8, D4, D2 and D1. So 0, 0, 0, 1, 1, 1, 1, 0, 0, 0 here, 0, 1, 1, 1, 1, 0. So at the place of 0 there is 1, right? And at place of 3, so 0, 0. So this one is 3, right? 0, 1, 2, 3, 4, 5, 6, 7, then 8, 9. Till 9 we have only, and all other places there is a don't care condition, right? Till 15. Okay, now we have to make, we can here make one chord. Then what will be the expression for this chord? 1 means D8. Here we can take common one, so D8. And from here 1 also, so D8, D1, right? The another one is we can make pair here. So what will be the expression? Here 1, so that means D4 and it is D2, D1 bar, D2, D1 bar. And another we make pair from here and here, right? So what will be the expression? Here D4 bar and D2, D1. And what? It cannot be make any pair, so it will be D8, D4, D8 bar, D4 bar, D2 bar and D1 bar. D8 bar, D4 bar, D2 bar, D1 bar. Now add all those things and we will get the minimum function that can detect divisible by 3. Okay, so let's see D8, D1, where I can write it. Here I am writing here D8, D1 plus then this one D4, D2, D2, D1 bar, not here bar, plus this one D4 bar, D2, D1, then this part D8 bar, D4 bar, D2 bar, D1 bar. So let's make option B is the correct answer. D8, D1, then D4, D2, D1 bar, then D4 bar, D2, D1, D8 bar, D4 bar, D2 bar, D1 bar. Option B is correct. This is the minimum function that can detect the divisible by 3 function in the BCD code. Okay. So I hope all of you got this questions, how we can solve it. Okay. Moving to the next question. So next question is the number of bytes required to represent the decimal number 1856757 in packed BCD binary coded decimal form. So number of bytes required. So 1 byte is equal to how many bits? We already know that 1 byte is equal to 8 bit. Yeah, 1 byte is equal to 8 bit. So these numbers, how many bytes represent these numbers? So total number here, how many? 7 digit. It is a 7-digit number, and it has, I can write more clearly. It has 7 digit. So every digit is represented by 4 bit. Okay. Every digit represents 4 bit. Total 7 digits. So 7 into 4 bits, right? Correct. So total number of bits is 28 bits, right? And 1 byte is equal to 8 bit. So how 28 bits represented by? So if we take 3 bytes, so 3 byte represents only 24 bits, right? And for another 24 bits, there is 28 bits. We need to take another byte. So total 4 bytes are required to represent this decimal number. So total 4 bytes are required to represent the decimal number. I hope all of you have got this question. Okay, I hope all of you are getting this question. So moving to the next and last question. So can anyone guess for this? Can you, so last question is the full form of the abbreviations TTL and CMOS in reference to logic families are. What is the full form? What are the full form of TTL and CMOS? First option is triple transistor logic and chip metal oxide semiconductor. Second option is tri-state transistor logic and chip metal oxide semiconductor. Third option is transistor logic and complementary metal oxide semiconductor. And fourth one is a tri-state transistor logic and complementary metal oxide silicon. Which one is correct? Yeah, correct. Option C or option 3 is the correct option. The full form of TTL is transistor logic, and the CMOS is complementary metal oxide semiconductor. Okay, so option 3 is the correct answer for this question. Okay, so today these are the some questions which may be similar to your assignment problems. Maybe it can help you. So the questions are completed. Now you can ask the doubts if you have any.
Ma'am,
Yeah,
that BCD code divisible by 3.
yeah.
So why we had considered 0 also function 1?
Because that can be divisible.
Matlab 0 can be divisible by any number then.
Yeah, 0. In that case, we are taking 0 because that can be divisible. If you are taking any other number, 5 also, if you take,
We'll consider 0.
you will consider 0. 0 will be considered
Okay.
in that case. Any other doubt you have?
Thank you. No, ma'am. Thank you.
Okay. Thank you, everyone. So, thank you for joining the session. Now you can leave the session. Okay. Yeah, maybe some other TA will be there, some other person will be, so that can we take the different questions. Actually, I don't know whether they are taking the some questions or different. There is a difference between the questions. Okay, Payal? Yeah. Okay. Okay, so thank you.